We will start in 2 minutes. Am I audible to you?
Yes, ma'am.
Okay, so we will start. Okay, okay, no issues. I will continue. You can join in again. So the first question is, in this week, the Saras taught about the heterogeneous catalysis, the ethyl benzene production, and isobutene production. So we'll be discussing around those topics. The first question is, heterogeneous catalysts are difficult to separate. Is it true or false? Heterogeneous catalysts are difficult to separate. Yes, it is. false, because here it is written that heterogeneous catalysts in continuous processes are often preferred in industrial catalysts for an engineering standpoint, and catalyst separation is easier with heterogeneous catalysis. So catalyst separation is easier in case of heterogeneous catalyst, and for homogeneous catalyst it is difficult to separate. So here it is false. So your answer is wrong. Noted. Next question is the what is important to select a catalyst? What is important to select a catalyst? Like what are the condition needs to be fulfilled to select a catalyst?
Shape, size, and porosity.
Catalyst size and shapes are important. Again, the reaction kinetics, like what catalyst should we choose based on the reaction kinetics, the reactions are happening. So for the phases of reaction, whether it is in gas phase or liquid phase, or the kinetics of the reactions and the diffusion rates of the reactions and reactants and products are also important, along with the catalyst size and shape. Okay. Third
Okay,
question.
ma'am.
Yes. Third question is that tiny particles are needed to lose the pressure drop in fixed bed reactor. Tiny particles are needed to lose pressure drop in fixed bed reactor. Is it true or false? Tiny particles are needed to lose pressure drop in fixed bed reactor. Is it true or false?
True.
No, it is not true, because big particles are, in case of tiny particles, what happens? The particle size is very small, so their surface to volume ratio is very high. So for that case, they have high pressure drop. Okay, so they have high pressure drop. So this is the pressure drop delta P by L. So this is very high in case of tiny particles. So for bigger particles, this S by V ratio is smaller, surface by volume ratio of a particle is smaller, and as well as the pressure drop is also reduced. So here it is false. Okay. Next question is the what is the internal effectiveness factor? What is the internal effectiveness factor? So, the definition of internal effectiveness factor is the ratio of observed reaction rate divided by reaction rate without internal gradients. So, that means that observed reaction rate means the reaction happens, observed reaction rate means the reactions happens at the active sites at different particle concentration. That means in a reaction when heterogeneous catalysts are used, so this kind of catalysts have some active sites where the reactions happens. In all of the catalyst particle, the reaction doesn't happen. It happens in particular active sites. So at that particular active sites, we are observing the reaction rate change. So this is the definition of the observed reaction rate. And divided by reaction rate without the internal gradients. It means the reaction rate at the surface we are seeing. That this is the surface outside the catalyst. So the reaction rate of the reactants, we are seeing the reaction rate of the reactant at the surface of the catalyst, and here it is the inside of the catalyst. So these two ratio is called the internal effectiveness factor. Next question is the what is the minimum value of internal effectiveness factor for diffusional resistance? What is the minimum value of internal effectiveness factor for diffusional resistance? What is the minimum value of internal effectiveness factor for diffusional resistance? So the answer is 1. For diffusional resistance, internal effectiveness factor is 1. Next question is what is the minimum value of Thiele modulus for insignificant diffusional resistance? What is the minimum value of Thiele modulus for insignificant diffusional resistance? What is the minimum value of Thiele modulus for insignificant diffusional resistance? You try to answer, I will give answer after 1 minute. So, what is Thiele modulus? The definition of Thiele modulus is phi equals to volume per surface area root under K kV then divided by D effective into n plus 1 by 2 Cs to the power n minus 1. So this is the definition of the Thiel modulus, where phi is the Thiel modulus, then V is the volume of the catalyst, AC is the surface area of the catalyst. Okay, for V by AC ratio is Rp by 3 for spherical particle. Why I am showing you that for sphere V equals to, you know the formula, 4/3 pi r cube, and surface area is 4 pi r square. So this volume by surface area ratio will be 4/3 pi r cube divided by 4 pi r square equals to this 4 will be cut out, this pi, this r square, but only the r is left and by 3. So this is the volume by ratio for a spherical particle. This is r by 3. Then Kv is the intrinsic reactant coefficient per unit volume. Okay, effective is the effective diffusion rate of the reactant molecules, and C is the concentration of the catalyst surface. Cs is the concentration on the catalyst surface. Okay, so there is a graph you have seen. Sir has taught already. This is the Thiel modulus versus internal effectiveness factor. So here the graph goes like this, right? So here it is 0 0.1, 0 0.5, then 1 like this, and here it is 0 0.1, 0 0.5, and here it is 1. Alright, so for diffusional resistance, the Thiel modulus value is 0 0.5. Okay, so here 0 0.5 will be right answer, and for that 0 0.5 you can see that the effectiveness factor is almost 1. Okay, that is why in the previous question it was, the effectiveness factor was 1. Okay, I think it is clear. Next question is, tiny particles are entitled to high heat transfer. Tiny particles are entitled to high heat transfer. Tiny particles are entitled to high heat transfer. Is it true or false? So the answer is true. It is obvious because in case of tiny particles, the surface to volume ratio of a particle is very high because they are very tiny particles. So all of the like the whole surface area of a tiny catalyst is can be used for the effective reaction. Okay, but if the size is very bigger, then uh, all of the particle cannot perform in the catalyst reaction. Only the active sites can perform. But in case of tiny particles, the whole particle can perform in the catalyst reaction. That is why its surface to volume ratio is high, and that is why they are more effective in catalytic reaction or heterogeneous catalytic reactions. So that is why the temperature distribution is uniform throughout these catalytic particles. Okay, because they are small particles, so the concentration distribution, the temperature distribution is very uniform around the particles, and the hence in the mixture also, the in the reactant mixture also, it provides good heat transfer or no temperature fluctuation. Okay, that is why tiny particles are entitled to high heat transfer. I hope this is clear. The next question is, bigger particles are inversely proportional to pressure drop in fixed bed. Bigger particles are inversely proportional to pressure drop in fixed bed. Is it true or false? Bigger particles are inversely proportional to pressure drop in fixed bed. Is it true or false? Here the answer is true, because the same reason, just I have said that in case of tiny particles, surface to volume ratios are high. So for bigger particles, it is obviously low. Okay. So surface to volume ratio is low, and hence the pressure drop per length, that is delta P by L, is also, this is pressure drop. This is also low. Okay, so in case of fixed beds, in case of fixed beds, we use bigger particles. Okay, we use bigger particles. That is why their surface to volume ratio is uh, small. That is why pressure drop is also small. That is why bigger particles, that means the size of the catalyst particle increases with decreasing pressure drop. That is why it is inversely proportional to the pressure drop. Okay, so that is why it is true. Next question is what is the particle size in a fluidized bed reactor to reduce attrition resistance? What is the particle size in a fluidized bed reactor to reduce attrition resistance? What is the particle size in a fluidized bed reactor to reduce the attrition resistance? So here the answer is 30 to 150 micrometer. So in fluidized bed reactors, the particle accretion means suppose there is a particle and it experiences some kind of force in the tangential direction. So due to that force, the particle size can be reduced. Okay, so this type of phenomena can happen inside a fluidized bed reactor because there are small particles. Okay, and here gas or any kind of fluid is coming, right? This is a fluidized bed reactor. So that is why if the particle size inside this bed is very big, suppose in millimeter scale. So that will lead to the attrition between the particles. That means the tangential friction between the particles, that will reduce the size of the particles and which will not serve our purpose. That is why we have to make the particle size very small. It is in the range of 30 to 150 micrometers, so that this attrition does not happen. Okay, so this is the answer. Next question is, the high reaction rate is associated with bigger particles. High reaction rate is associated with bigger particles. Is it true or false? So the answer is false. For the same reason that it has low surface to volume ratio, that is why they are not very effective for high reaction. So if it is a smaller particles, it will be high. Okay, so this is false. Next question is, what are the parameters of a heterogeneous catalyst reactor? What are the parameters of a heterogeneous catalyst reactor? So what are the parameters of a heterogeneous catalyst reactor? So there are 5 parameters. The first one is the number and the kind of phases. The number and the kind of phases. That means in case of heterogeneous catalyst, the catalyst is solid, of course, but in the reaction there may reactants may be in gas phase or liquid phase, and the product also may be in gas phase or liquid phase. So first we have to take care of the number and kind of phases, whether it is gas, whether it is liquid phase reaction. So we have to notice that, and we have to know the volume fraction of the individual phases. This is the first parameter of a heterogeneous catalyst reactor. The second one is the mixing and contact patterns. So, how the reactant is mixing with the heterogeneous catalyst is to be noted here. Okay, so how it can come in the co-current method, counter current method, or the cross current method. Okay, so based on these three type of methods, we can choose the mixing and contact patterns. The third one is the reaction kinetics. That is the primary and side reactions happenings in the particular reactor is to be noted here. For that we need to maintain certain temperature, certain concentration of a reactant, and certain pressure of the reactant, right? So in that optimal concentration, optimal pressure and optimal temperature, the reactant will give the desired product. So we have to maintain that. So for that we need to know the reaction kinetics. This is the third point. The fourth one is the reaction enthalpies. So this is the how the heat transfer is happening in the reactor. It will be considered by the reaction enthalpies, whether the heat is needed to be supplied from the external field or from the exothermic reaction. We will collect the heat and use it in endothermic reaction, or either of the ways. Okay, so we need to know these factors before the reaction can start in a heterogeneous catalyst reactor. And the last point is the deactivation of the catalyst. That means that how often the catalyst is added or removed, we need to know. Okay, so deactivation can happen for many reasons. Maybe the catalyst particles, uh, the size of the catalyst particle will be reduced because of the attrition, or they are poisonous for the reaction, so they needs to be taken out repeatedly. Okay, or because of the coke deposition, that catalyst can be deactivated. So how often we need to change the catalyst is also our important parameter for the heterogeneous catalyst reactor. So these are the 5 main points. The next question is the what is the most popular form of reactor in industry? What is the most popular form of reactor in industry? What is the most popular form of reactor in industry? So this is the answer is adiabatic fixed bed reactor. Okay. In adiabatic fixed bed reactor, actually it is important because the temperature is maintained here. Okay. So no thermal fluctuations are happening in adiabatic fixed bed reactor. That is why it is more preferred in the popular form of reactor in industry. The next question is catalysts are randomly placed in adiabatic fixed bed reactor. Catalysts are randomly placed in adiabatic fixed bed reactor. Is it true or false? So here the answer is true. Catalysts are randomly placed in adiabatic fixed bed reactor. That is why it is most preferred in industry. Next question is what does it mean by moving bed catalysts? What does it mean by moving bed catalysts? So the answer is regenerative catalyst. Okay. Moving bed catalyst means regenerative catalyst. That means the catalyst is regenerated in each step. Okay. So catalysts are not wasted here. It is getting regenerated every time. So that means the moving bed catalyst. Next question is which is the prevalent type of flow? Which is the prevalent type of flow? So the prevalent type of flow is downward flow. That means it is very common actually, because there is, suppose there is a bed, fixed bed, and your feed is coming from here and product is getting collected from here. So that is why it is called as downward flow. Okay. The next question is which type of flow is used to reduce the pressure drop? Which type of flow is used to reduce the pressure drop? Which type of flow is used to reduce the pressure drop? So the answer is radial flow. So what is the structure of the radial flow? Suppose this is a reactor. Okay. So feed is coming and this is going here and this is going here, and this is kind of rotational motion it is creating, and from here it is also coming. Okay. Okay. And now here it is getting the product. So radial flow happens in the happens like this in rotational motion, and that is why it reduces the pressure drop of the bed. So that is why radial flow is used. Okay. So this is the structure of the schematic diagram of the radial flow fixed bed. Next question is in fluidized bed liquid is coming from top. Is it true or false? In fluidized bed liquid is coming from top. In fluidized bed liquid is coming from top. So it is false. Okay, in fixed bed the fluid is coming from top, but in fluidized bed, so this is fluidized bed, there are the catalyst solid particles and fluid is always coming from the top and product is collected from top. Okay, so in fluidized bed, fluid, that means liquid or gas, whatever it always comes from the bottom. Okay, so it is false here. The next question is, steam reforming happens in which of the following reactor? Steam reforming happens in which of the following reactors? Answer is simple fixed bed reactor. There are multiple reactions happens in the catalytic reforming, methanol synthesis, hydrodesulfurization, along with steam reforming happens in the simple fixed bed reactor. So here the answer is simple fixed bed reactor. Next is the ammonia synthesis happens in fluidized bed reactor. Is it true or false? Ammonia synthesis happens in fluidized bed reactor. The answer is false, because ammonia synthesis happens in simple fixed bed reactor. Okay, so it is false. Uh, Question number 20. Ethanol synthesis happens in which of the following reactors? Methanol synthesis happens in which of the following reactor? Methanol synthesis happens in which of the following reactor? The answer is simple fixed rate reactor and radial flow reactor. In both type of the reactors, ethanol synthesis happens. Next, modern FCC process happens in entrant flow reactor. Modern FCC process happens in entrant flow reactor. Is it true or false? So modern FCC process happens in entrant flow reactor. It is true. So what is entrant flow reactor? So Till now we have studied about the fixed bed reactor, fluidized bed reactor and entrant flow reactor, right? So this is the fixed bed reactor. Feed is coming from here. Here are the particles, bigger size, little bit bigger size particles, and fluid is coming from here, and they have the reaction inside this in this phase, and product is collected from here. Okay, this is the fixed bed. Now what is fluidized bed? In case of fluidized bed, I just told that the catalyst particle, solid catalyst particle size should be smaller. So here are this. From the bottom, fluid is coming, okay, and at a certain flow rate, the reactions happens here, okay, and this bed got expanded. If we increase the fluid flow rate of the gas or fluids or the liquid uh, at a certain pace, this bed will expand to this, okay, and it will create a homogeneous kind of mixture, okay, and product will be calculated collected from the top, and this is called the fluidized bed. So in the fixed bed, this bed does not expand. It remains as it is from start to finish. But in case of fluidized bed, the smaller particles, because they have very less mass, so they will expand. They will behave like a fluid, and they will expand after a certain flow rate of the inlet, okay, inlet flow, that is a gas or liquid. So they can expand in fluidized bed. So that is why it is called fluidized bed. And if this fluid velocity is very high, okay, this is extremely high, suppose, then what will happen? There will be a violent mixture of this fluid and these solid particles, solid catalyst inside the bed, right? There will be a violent mixing of this, okay, violent chaotic vigorous mixing of these solid particles and the fluid that is entering from the bottom. And due to this chaotic mixing, there is no direction of the particles where will they go, and that and this bed will expand throughout the size of the reactor, okay, this bed will expand, but after some time you will see that at very high flow rate, this some of the particles will fall out of the bed, okay, some of the particles will fall out of the bed. They are fine particles, because we have seen that there are fine particles in the fluidized bed or smaller size particles in the fluidized bed. So some of the particles may fall out from the fluidized bed, okay. So this situation is called entrant flow reactor or entrant flow bed, whatever it is, okay. So these are the three conditions here. In case of fixed bed, the bed doesn't expand. In case of fluidized bed, the bed starts expanding after a certain velocity it achieves. And in case of entrant flow bed, the inlet flow rate should be very high, and some of the solid particle or catalyst particles will flow out from the top of the reactor bed. Okay, this situation is called entrant flow bed. I hope this is clear. Next question is, what type of reactors are used for hydrogenation of residues? What type of reactors are used for hydrogenation of residues? The answer is moving bed reactor and three-phase fluidized bed reactor, where hydrogenation of residues happens. Next question is, the low pressure drop in a reactor is ideal for gas phase reactions. Low pressure drop in a reactor is ideal for gas phase reactions. So the answer is true. Low pressure drop in a reactor is ideal for gas phase reactions. And to maintain a low pressure drop, what we need? We need low surface to volume ratio. So for that we need bigger particles, and for that we need fixed bed reactor. Okay. Next question is, what is entrant flow reactor? What is entrant flow reactor? So I have just discussed what are the three different types of flows. So you can copy paste it here. Okay. So I just discussed what is entrant flow reactor here. So it will be clear from here. Next question is, the zeolite catalyst has a high activity. Is it true or false? Zeolite catalyst has a high activity. Is it true or false? So zeolite catalyst has a high activity. It is true. That is why zeolite catalysts are mostly used in a heterogeneous reactor. The second, oh, sorry. Thermal insulators are used as catalysts in fluidized bed reactor. Thermal insulators are used as catalysts in fluidized bed reactor. So we have already seen the answer. It is false. Thermal insulators are used as catalyst in fixed bed reactors. Okay. So that is why it is false. The next question is what is called when catalyst it is thermally deactivated? What is called when what is called the process when the catalyst is thermally deactivated? So the answer is sintering of the surface area. Sintering of the surface area. The next question is to decrease the feed conversion, hydrogen is added in a reactor. To decrease the feed conversion, hydrogen is added in a reactor. Is it true or false? The answer is true. To decrease the feed conversion, hydrogen is added in a reactor. The next question is what type of process happens in multiple fixed bed reactors? What type of process happens in multiple fixed bed reactors? What type of process happens in multiple fixed bed reactors? The answer is semi-regenerative. Okay, not fully regenerative because fully regenerative type of process happens in multiple fixed bed reactors with swing reactor. But I have only asked here for multiple fixed bed reactors, so it is semi-regenerative. The next question is majority of the solid catalysts are class selective. Majority of the solid catalysts are class selective. Is it true or false? The answer is true. Majority of the solid catalysts are clash selective. Next question is, what is zeolite? What is zeolite? So, zeolite is a group of crystalline microporous particles constructed from regular networks of alumina and silica tetrahedra. Okay, in zeolite, mostly Al3 plus, Si4 plus ions are available. Okay, so it is a group of crystalline microporous particles constructed from regular networks of alumina and silica tetrahedra. And the tetrahedral bond is constructed by oxygen. Okay. It is the zeolite. Next is, what is the pore size of zeolite particles? What is the pore size of zeolite particles? The answer is sub 2 nanometer pores, because zeolite particles are porous particles, microporous particles. Okay, so suppose this is a zeolite particle, so it has porous. Okay, so these are less than 2 nanometer pores. Next question is, what is the content of methyl tropinium? What is the content of methyl tropinium? What is the content of methyl tropinium? The answer is Na plus, sodium ion. So ZSM 58 is a zeolite which is made of using methyl tropinium and methyl tropinium in a classic gel. Methyl tropinium is a classic gel which contains Na plus. So the answer is Na plus. Next is, the small products diffuse through zeolite. True or false? Small products diffuse through zeolite. The answer is true. Small products diffuse through zeolite because zeolite contains micropores which is in nanometer range size. So very small products can diffuse through zeolite. It is true. Next question is, what are the shape selectivity of zeolite? What are the shape selectivity of zeolite? What are the shape selectivity? Like what are the categories of shape selectivity of our zeolite? The answer is three. There are three categories: reactant type, transition state type, and final product type. In the reactant selectivity, what happens? Molecules with dimensions smaller than the pores may enter and react in a mixture of feed molecules. So, any kind of reactant which size is more than the pore size of a particular zeolite cannot react. So, here it is the reactant selectivity. Transition state selectivity, paths with certain transition geometries will be functional. Okay, and in final product means there are two kind, maybe there are multiple products coming from a reactant, coming from a reaction. So the product size passing through the zeolite will be collected, and the bigger size product which cannot pass through the zeolite will be there in the reaction. So that is the final product selectivity of zeolite. Next is the MTBE, methyl tert butyl ethanol, is used to increase the knock resistance. Methyl tert butyl ether is used to increase the knock resistance. It is true or false? The answer is true. MTBE, ETBE, they are used to increase the knock resistance. What are the reactants of MTBE and ETBE? What are the reactants of MTBE and ETBE? So the answer is methanol or ethanol. So this is isobutane, right? This is isobutene. It is like C, there is CH3, there is CH3, and here it is CH2. This is the isobutene. Reacts with methanol, produces MTBE, that is the methyl tert butyl alcohol. So its structure is this, right? So here it is CH3, 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 it is C, here it is CH3. This is the MTBE, and similarly this isobutene reacts with ethanol, CH3, CH2, OH, produces ETBE. Okay, this is MTBE and this is ETBE, ethyl tert butyl ether. Next question is the discuss the roots of isobutene. Discuss the roots of isobutene. So there are two steps. First there is N-butane. Here happens isomerization. It produces isobutane, and after dehydrogenation it produces isobutane. Another way, N-butene, after doing the isomerization, can produce isobutane. So there are two ways of producing isobutane. Next question is, what catalyst is used for isomerization of butane? So from this butene to isobutene formation is used the catalyst ferrierite. Okay, this is a one type of zeolite. Next question is, what is the temperature of the reactor maintained in N-butene isomerization? What is the temperature of the reactor maintained in N-butene isomerization process? The answer is 620 Kelvin. So here in the reactor, the feed is coming. The feed is N-butene. Okay. Here the catalyst is given ferrierite. And the temperature is maintained at 620 Kelvin and 1 to 2 bar pressure. And from the bottom of the reactor, the product is collected and it is passing through a compressor and went into the distillation column. This is a distillation column. So from the top of the distillation column, we collect the C4 product, that is the isobutene after isomerization, and from bottom we are collecting the byproducts, other hydrocarbons which has more than 5 carbons. Okay, so they are collected from the bottom and they will go to the gasoline pool. Okay, so the temperature is 620 Kelvin in the reactor. Next question is, what is the product distribution of the isobutene isomerization reaction? What is the product distribution of the isobutene isomerization reaction? So in this reaction, what are the product distribution? So along with the isobutene, mostly the 35% of the product is isobutene. Okay. the 40% of the product is N-butene, which will be recycled again in the reactor to for another isomerization process, and the rest 5% is the hydrocarbons which have only one carbon to three carbon chain, three carbon in the hydrocarbon chain, and the rest 20% is the C5 plus carbons, hydrocarbons. Okay, so this is the product distribution of the isomerization reaction. Next question is, the isobutene isomerization reaction happens in liquid phase. Is it true or false? Isobutene isomerization reaction happens in liquid phase. Is it true or false? The answer is false. Isomerization reaction always happens in gaseous phase. Okay, so this is false. Next question is an example of transition state selectivity of zeolite. An example of transition state selectivity of zeolite. The answer is disproportionate of M-xylene. What happens in M-xylene gives trimethylbenzene plus benzene, right? Xylene. Trimethylbenzene and benzene. So three type of trimethyl benzene can be produced: 1,2,4 trimethyl benzene, 1,3,5 trimethyl benzene, and 1,2,3 trimethyl benzene. But due to the sterically hindered coupling geometry, only one kind of trimethyl benzene is produced. This is the state selectivity, transition state selectivity of the zeolite. I will show the example given in the lecture. So here, so this is the metaxylene, and after the reaction it produces 135, but it is not the but it is not the expected one. Okay, so it produces 1,2,5 trimethyl benzene. Okay, so this structure is not accepted even if the molecular formula is same for both of the cases, but here it is not produced, but 1,2,5 is 1,2,5 is produced. Trimethylbenzene is produced. So you can see in the transition state itself, it is decided whether this will be formed or this will be formed. Okay, so this is how zeolite uh, occurs. Next question is the, so this is a transition state example is a disproportionation of enzyme. Next question is that the conversion of butene to isobutene with ferrite proceeds with what? In which order? Like what will happen when we add ferrite in butane? So first the dimerization happens. So this ferrite is a zeolite catalyst which has medium-sized pores, and first dimerization happens to yield a C8 intermediate, which then undergoes skeletal isomerization. So from here it is skeletal isomerization. हेलो. हाँ दिशांक से आ रहा है 10 मिनट में आ रहा है. एक मिनट एक्चुअली मैं क्लास में हूँ तो 10 मिनट में खत्म हो जाएगा. आप थोड़ी देर रुकिए या नीचे दे सकते हैं क्या इसमें आपका अगर जल्दी हो तो. अच्छा अच्छा ठीक है ठीक है. So the second one is the skeletal isomerization, and skeletal isomerization, and last the selective cracking. Last point is the selective cracking happens to produce two isobutene molecules. So this is the process of using ferrite. Okay. Next question is the alkylation reaction are independent of temperature and pressure. alkylation reaction are independent of temperature and pressure. Is it true or false? So here I need to mention alkylation reaction of the benzene I have asked. Okay. So benzene alkylation reaction are independent of temperature and pressure. Is it true or false? The answer is false. So in benzene, when alkylation happens, it happens with ethene produces ethyl benzene, right? This is the alkylation reactions. So alkylation reactions are exothermic and it is thermodynamically favored by low temperature and elevated pressure. So it is not independent of temperature. So it is false. Next question is what is the physical condition of transalkylation? What is the physical condition of the transalkylation? So the answer is independent to temperature and pressure. So what happens? Benzene reacts with ethene, produces ethyl benzene. Then in it again reacts with ethene, produces diethyl benzene. Okay, this is diethyl benzene, and if this ethene gets adding with this benzene or ethyl benzene, it will produces polyethyl benzene. We don't want to do that. So from the diethyl benzene, we want to add more benzene so that it will produce ethyl benzene only. So because our desired product it is ethyl benzene here. Okay. So this process is called transalkylation, and this process is independent to temperature and pressure. Next question is oligomerization is mainly responsible for the byproducts. Is it true in ethyl benzene reaction? Is it true or false? Oligomerization means adding of two ethene molecules in the benzene, that is forming the diethyl benzene. Okay, so oligomerization is mainly responsible for the heavier aromatics or byproducts. It is true, and it produces butyl benzenes, diphenyl compounds, and heavy aromatics. Okay, so it is true. The next question is what are the contaminants of ethyl benzene fuel? What are the contaminants of ethyl benzene fuel? So we don't want to produce diethyl benzene or higher ordered ethyl benzene, right? So these are the contaminants for ethyl benzene free, that is butyl benzene and diphenyl compounds are the contaminants of this reaction. Next question is the conversion of benzene decreases with increasing ethene to benzene ratio. Is it true or false? Conversion of benzene decreases with increasing ethene to benzene ratio. It is false because benzene will convert if we increase the ratio of ethene on benzene. That means more and more ethene will be added to benzene and benzene will be converted. So conversion of benzene will increase. So here it is false. The last question is the what is the catalyst used in ethyl benzene alkylation process? What is the catalyst used in ethyl benzene alkylation process? So in liquid phase alkylation process, aluminum chloride is used, AlCl3, and gas phase alkylation process, zeolite ZSM5 is used. Okay, ZSM5 is used. So that is from my side. So you have to remember this ethyl benzene liquid phase reaction flow chart. What is the Monsanto-Lummus process? That is the liquid phase alkylation method, and this Mobil-Badger process, that is the gas phase alkylation method, where the zeolite is used, ZSM5 zeolite is used. So this two process needs to be remembered for exam. Okay, so the question answer session is done. So that is from my side. Hope you will find this helpful, and till then, goodbye and thank you for joining.